All right, now we're going to consider the motion of a charged particle in a magnetic field. We've talked about the force on the particle, but now we get to think about the actual motion as a result of the force. And it's pretty cool the way it works out. Turns out it goes in circles or in actual spirals if there's a component of the velocity along the magnetic field. All right, so let's look at the electrical case. If we have an electric field, the force, and let's say we have a positive particle, and it's moving in a particular direction v, as shown here. What's the direction of the force? Well, the force is Q times E. So the force and the electric field are parallel to each other if the charge is positive. Force and the electric field are opposite to each other if the charge is negative. But we're talking about a charged particle. So that force is going to be in the direction of the electric field. And so that charge that comes in perpendicular to the electric field initially experiences a force that pushes it in the direction of the field and curves it around until it's starting to head in the direction of the electric field. What about in the case of a magnetic field? So we have North Pole here and South Pole here, and like we talked about before, the magnetic field lines begin at North Poles and end at South Poles. So this might be just the faces of a big horseshoe magnet. Remember, you can't just have an isolated North Pole, so there must be another magnet armature that comes around here to create this situation. The magnetic field lines are shown here to the right on the screen. And this is our charged particle again. And here's the direction of its velocity. Well, we're going to have a velocity in this direction, a velocity given by my thumb. It's a little hard for you to see. Here's my thumb pointing in the direction of the velocity. And then my fingers pointing in the direction of the magnetic field. And then the force is going to be up. And it's going to cause this charge to bend in a circle. As it turns out, if it stays within the field, it will continue to go in a circular pattern, whereas this guy won't. Eventually, this charge will be heading in the direction, asymptotically in the direction of the electric field. And the magnetic force can't do work on the charged particle, and the reason is, if you think about work from last semester, the work that's done on an object is zero if the displacement is perpendicular to the force. So the work done by a force that's perpendicular to the displacement, perpendicular to the velocity, must be zero. In this case, the force and the velocity are always perpendicular to each other. Here the velocity is in this direction and the force is up. Here the velocity is up and the force is horizontal. They're still at a right angle with each other. So you can't change the velocity of a charged particle using a magnetic field. You can with an electric field. All right, a charged particle is moving through a constant magnetic field. Does the magnetic field do work on the charged particle? The answer has to be no. And the reason is because it's always perpendicular to the velocity, because the force is always perpendicular to the velocity of the particle. All right? This is used in objects called velocity selectors. So it's a device for measuring the velocity of a charged particle. The device operates by applying electric and magnetic forces to the particle in such a way that these forces balance. How should an electric field be applied so that the force it applies to the particle can balance the magnetic force? Well, let's take a look. We've got a velocity to the right here. These x's represent the magnetic field pointing into the paper. So since it's all 3D with magnetic fields, we have to find some way of denoting whether a field is into or out of the paper. And the way that we denote into the paper is by using these little X's. And the way that I think about them is I think about the magnetic field vectors being into this paper or into the screen in this case. And I think about this being like the feathers from the arrow on the back side of the arrow. You can think about it however you want to. But I'm just thinking about looking at the back side of this arrow that you'd use for your bow and seeing the feathers. So I think about it that way. If you want to denote a magnetic field that's out of the paper, and we'll do that also, that's denoted this way, a little dot. So that's denoted by a little dot with a circle around it. And I think about that, the magnetic field's coming out, right? So I think about that being the tip of the arrow, this little dot being the tip of the arrow that's just puncturing the screen or the paper. Think about it however you want. That's how I think about it. So, but in any case, in this particular problem, we have a positive charge. That makes things a little easier because it comes out of the palm. We have a velocity to the right, and I'm going to put my thumb in the direction of the velocity, as I hope you can see. And then I'm going to have to point my fingers in the direction of the magnetic field. How do I do that? Well, the magnetic field is into the paper, so I don't want to come this way. I want to come that way. So now my thumb is pointing in the direction of the velocity, and my fingers are pointing into the paper. What's the direction of the force now? It's out of my palm. So the force is going to be up. For a positively charged particle, and sure enough, this is a positively charged particle. So it's going to experience a magnetic force. Let me just put Fm to denote that magnetic force that's up. And what we're trying to do is apply an electric field so that the net force will be 0. So I want an electric force. This subscript E just means that that's the electric force. I want an electric force that's down to balance out that magnetic force that's up. Well, what direction does the electric field have to be in for the force to be down? The force is Q times E, and if the charge is positive, then the electric force is in the same direction as the electric field. The electric field has to be in this direction. And so we're going to put our positively charged plate up here and our negatively charged plate down here because electric fields begin on positive charges, right? And they end on negative charges. So that's how to do that kind of problem. Let's talk about a cyclotron. The magnetic force always remains perpendicular to the velocity and is directed toward the center of a circular path. This is what physicists call a central force. So what we're going to do is to derive the cyclotron radius. So here's a positively charged particle. Here's its velocity to the right. Let me let you, and there's a magnetic field that's into the paper. So let's verify this direction of this force. And you know you've actually got a 50-50 chance to get the force right. But I don't want any of my students. You're going to be stronger than that. You know, it has to be perpendicular to the plane that contains the velocity and the magnetic field. Magnetic field is into the screen. The velocity is to the right. So let's do it. The velocity is to the right, so I got to put my thumb toward the right. I got to put my fingers in the direction of the magnetic field that's into the screen. So my fingers are pointing into the screen, and the force therefore has to be toward the top of the screen. All right, but the same thing happens over here. The velocity now is in this direction, and now we're going to do thumb in the direction of the velocity, fingers in the direction of the magnetic field that's into the screen, and the force is this direction. Force and velocity always perpendicular to each other, so it does no work. And that's a central force. That's just like gravity. When you have an object that's in circular orbit around the Earth, the force always points toward the center of the circle. We have a specific name for those kinds of forces. And then what is it? It's called a centripetal force, a center-seeking force, always toward the center. And we normally denote it as F sub c. What is that centripetal force? Well, it's the magnetic force. And it's supposed to equal the mass times the acceleration of that object that's going in this circle. So if you're going in a circle of radius r, and you have a speed v, that's the magnitude of the velocity, the acceleration is toward the center of the circle. It's called uniform circular motion. We talked about it last semester. And the acceleration has to be v squared over r. I'm sure you all, if you don't remember it, maybe it's coming back to you a little bit. This is just F equals ma, where a is right here, the acceleration. The centripetal acceleration is v squared over r. Well, what's that central force? It's a magnetic force. And how are we going to find it? Well, we know that its magnitude is q v b sine theta, where theta is the angle between the velocity and the magnetic field. What's the direction of the between the velocity and the magnetic field being into the screen and the velocity being to the right? Well, it's 90 degrees. What about here? The velocity is toward the top of the screen, and the magnetic field is still into the screen. Again, still 90 degrees. So theta is 90, and we're going to have the sine of 90 degrees. Well, what's the sine of 90? You say, hey, it's 1. And so, and this just gives us 1. So we get for the force Q, V, B times 1, which is just QVB. So we're going to put that in here and assume that the charge is positive, so I can replace the absolute value of a positive number is the same as that positive number. So we're just going to put Q in here. QVB is mv squared over r. And what we're supposed to find here is the cyclotron radius. What's the radius of this guy if he's going at a certain speed? Well, some simplifications happen here. We've got a v squared right here, and I got a v right here. So let's divide both sides by v. That kills this v and kills one of these v's. We're interested in the radius. And how are we going to find it? And the answer is we can multiply both sides of the equation by r. That cancels the r on the right-hand side, and we'll have an r times q times b. If I want to solve for r, I'm going to have to divide by q times b. And that gives us r on the left-hand side with mv divided by qb on the right-hand side. So that's a derivation. I never can remember this result, and I don't encourage you to remember it. I encourage you to be able to just derive it when you need it. It's a straightforward application of the principles of uniform circular motion and centripetal force. Well, what does it say? It says that the higher the speed, the faster this particle is moving, the bigger the radius is going to be. What about the magnetic field? The stronger the magnetic field it's going through, the stronger the centripetal force is going to be, and the smaller the radius is going to be. So this is actually seen in bubble chambers, as well as in aurora. The auroral lines are magnetic. And let me also say one more thing. If this is the direction of the magnetic field, what we've just described is motion perpendicular to the direction of the magnetic field. And the particles execute circles. If there's a component of velocity in the direction of the magnetic field, then the particles will actually execute spirals or helices. So it comes around in a spiral motion, and that is what particles do in the aurora. As highly energetic particles come in from it's called the Van Allen radiation belts, they spiral in around the magnetic field lines in tighter and tighter circles as the magnetic field gets stronger and stronger. Then those particles ram into the Earth's atmosphere and cause electronic transitions in the molecules that give off light, that produces the aurora. Same kind of thing in bubble chambers. So we've got an event that creates some charged particles, and they're heading out into space, but there's a magnetic field. And in this case, it's out of the paper. So we don't actually have the circles around these magnetic fields. We just have the dots that denotes a magnetic field that's out of the paper. Well, we're supposed to ask, so the particles are moving in this direction. So that's the velocity. And we're trying to determine the sign of each particle and which particle is moving most rapidly. Well, what about this particle number 1? Its initial velocity was toward the right like this, but it got deflected upward. So that must mean that the force on that particle, the magnetic force, was in this direction perpendicular to the velocity. Well, let's look if the magnetic field is out of the paper. Let's use the right-hand rule to try and determine the direction of the force, assuming the charge is positive. I've got to put my thumb in the direction of the velocity, and then I've got to put my fingers in the direction of the magnetic field. Well, what's the direction of the field? Well, it's out of the paper, out of the screen. So I've got to orient my hand while keeping my thumb pointing in the direction of the velocity, orient my hand until my fingers are pointing in the direction of the magnetic field, which is out of the screen. And then the palm of my hand gives the direction of the force on a positively charged particle. So that's actually the case for this particle too. It must be positively charged. The deflection of that particle, it was moving this way, it got deflected downward, down toward the bottom of the screen, and that one must be positively charged. This particle 1 must be negative. Why? Because it moves in the direction opposite given by the right-hand rule. Therefore, the charge must be negative. Why do they spiral in like this? It's because they're losing energy. So they're losing speed, and as they lose speed, the radius of their orbit gets smaller and smaller, and they spiral in. Now let's talk about assuming that particle 1 and particle 3 are both, they both must be negatively charged. Here's the direction of the velocity. And so it gets deflected less. It's in a circular orbit, but it's a big circle. It's going to be bigger than the screen. And so what does that say if we have a large radius? And going back to this slide, if the radius is large, then that speed must have been large, because the magnetic field is the same for the two particles. So particle 3 must have a high velocity, at least higher than particle 1, assuming that their charges are both the same. All right, an alpha particle, helium nucleus, which has a net positive charge. So it's a positive charge, that's what matters in this problem, is moving due east when it encounters a magnetic field is directed due north. Which of the following statements best describes the motion of the alpha particle after entering the magnetic field? Well, let's do it on the screen here. This is actually similar, in fact it's identical to the example we did before. Here's north, south, east, and west. And then up is in what direction? If this is considered a horizontal plane, then up would be out of the screen, right? And down would be into the screen. All right, so it's moving due east. It's a positively charged particle, and the magnetic field is directed toward the north. That's denoted by B. V, thumb in the direction of V, fingers in the direction of B, the palm points out, so the force on a positively charged particle must be out of the board, out of the screen, which is up. If this is a horizontal plane, I'm talking about looking down on the ground here with the cardinal directions mapped out here, then out from the ground must be up toward the sky. So it must be up. So that force is up. So this particle is going to be going east, and there's a deflection on it, which deflects up. So it's going to deflect up. It's going to continue to circle around that magnetic field until it comes back to where it started again. So this is going to be the motion of that positively charged particle. And let's see if one of these answers can capture that. Decelerates when we're not considering loss of energy here. The particle continues at constant speed, but direction changes as it follows a circular path. Well, this is actually true, and we know what that circular path is. It's going east. It experiences a force that's up out of the screen and then executes these vertical circles. Particle continues at constant speed, but direction changes as it follows a parabolic path. Well, no. It's going to be a circular path like we talked about before. A particle slows and changes direction. Okay, that's how to do these kinds of problems. Mass spectrometer, a very important application, and for you chemists out there, those that have worked in labs, some have dealt with mass spectrometers. Very expensive, but very, very powerful. They're used to determine the mass of particles. And how do they work? You have a source of ions here, you produce them somehow, and they are shot, they are accelerated through a potential. So they're given a certain velocity here, and then there's a magnetic field pointing out of the paper, so this is the velocity, V, B, and if it's a positively charged particle, the force will be to the right. And then there's a detector spaced at a distance of 2 times the radius of this circle. So here's one radius, here's 2 radii. You place that detector at a certain spot and you collect the particles. That allows you to determine what the mass of the particles is because you know the magnetic field, you know how fast it's going initially, and you're determining the radius. So basically what you do is you adjust the magnetic field until the particle of interest enters the detector. And having found that value of the magnetic field, you know the potential difference. This is this potential difference voltage here. And you know the radius because you know the distance between these 2 points, and that allows you to determine the mass. And we found that using the concept that we just covered, MV or QB, and then also using conservation of energy. from the last chapter. We have the change in kinetic energy equals the change in the potential energy, electric potential energy, which is E times the voltage from the last chapter. Putting all those things together is how you get a mass spectrometer. And you see, as you vary, as I said, as you vary B, you can see the output from the mass spectrometer, the abundance of different isotopes, which have different masses.